Okay, this is Jim Head. Welcome to our eighth in the series of the Origin and Evolution of the Moon, co-sponsored by us here at Brown University, Jim Head and David Kring at the Lunar and Planetary Institute, and in particular in relation to our SSERVI hosts. So today we're going to be talking about lunar Mare volcanism, complementing a lot of the previous discussions that we've had on the characteristics and origin of the Moon, the deep nature of the deep interior, the evolution of the crust that we heard last week, and other aspects of the origin and evolution of the Moon. So let me press on and talk about the essentially lunar Mare volcanism, in particular the emplacement of secondary crusts on the Moon. This is really an exciting topic because, in fact, most of the landing sites for Apollo were indeed in the lunar Mare, some in the highlands, of course, but it's a really critical aspect of the origin and evolution of the Moon. And so we want to spend today talking about a lot of these details. Where does the Mare come from? How do we recognize the emplacement characteristics? What are the ages, and so on? So when we take a look at this Earth-based telescopic view of the near side of the Moon, you can see that in fact they're the dark Mare and the light highlands. And there's a lot of diversity in terms of the albedo alone of the lunar Mare. Some of them are related to pyroclastic deposits, whereas others are related to just variations in titanium content and other characteristics of the lunar Mare. And David Kring really encouraged me when we started talking about the beginning of this course, organizing the course, to think critically about the phases of the exploration and understanding of the Moon. Particularly, what did we think, say, at the beginning of the awareness of the Moon, and how has our ideas changed since that time? So I want to talk about that a little bit first to set some background. And an important thing to think about here as we go into this first phase is try to think about what you know now, which is a lot about the lunar Mare, but also what are we going to know in 40 or 50 years? Clearly it'll be different. What are the challenges that you face? What kind of data do we need? And how do we change our view of the Moon as much today as it has been changed in the last 50 years? So when we take a look at this again, we can start by thinking about the pre-Apollo era prior to 1969. So, of course, Galileo first turned his telescope to the Moon and looked at the Mare as seas, literally the Mare and the highlands. Mare is seas in Latin. This is a first-order view, telescopic view, really important new ideas, and it was sort of an analog to what we see on the Earth, with the flat areas being water. And that view held forth for quite a while, and for decades and hundreds of years, actually, only telescopic views were able to be obtained, and of course, near side was the only thing that we could see. We could not see the far side of the Moon. So the detailed increase in capabilities of telescope led to a huge number of debates. The craters that Galileo actually described in 1609 were really argued in terms of their origin. Many people believed, such as Gilbert Fielder, that these were volcanic in nature, even the large craters like Tycho and Copernicus and so on. And Ralph Baldwin, a really key person in the early history of lunar exploration, found out that they were, in fact, just leave it open, found out and argued, in fact, that they were of impact origin. And that debate continued on right up to the Apollo era and even after. If you want to find a really interesting paper, go Google Jack Green, JGR, and the paper title is Copernicus as a Lunar Caldera. So it's a really great paper to read because it makes the argument that Copernicus, in all its characteristics, is related to a caldera, not an impact crater. So that debate continued on, and of course the origin of the Moon, was it accreted cold or hot? Harold Urey, a Nobel Prize winner, a famous geochemist, in fact one of the founders of essentially cosmochemistry, argued that in fact it accreted cold. And so there's lots of debates right up to the time of Apollo. The Mare were indeed thought by some people, particularly Tommy Gold, to be electrostatic dust deposits. He felt that electrostatic forces caused the dust to travel downslope, and that it collected in the lunar Mare, and the Mare were really extensive dust deposits. And these, the astronauts, when they landed on the surface of the Moon, would sink into this dust for basically, initially he thought tens of meters. Not a very good idea. Then in 1959, the Soviet Luna 3 got images of the far side and showed indeed that the near side and the far side were quite different from one another, particularly in terms of the distribution of the Moria. And then, of course, there were 21 Apollo precursor missions, Surveyor, Lunar Orbiter, and Ranger, and these provided really important information on the characteristics of the moon as we worked our way up to Apollo. During this time, the USGS had a comprehensive lunar mapping program, telescopic-based, and this really provided the basis where Gene Shoemaker talked about the stratigraphy of the moon, with the Imbrium Basin being essentially a timeline, a big impact, which set the stage for events post-Imbrium and pre-Imbrium, and that was really fundamental in our understanding of the moon. So there was lots of controversy. We didn't know whether the moon was hot or cold, argument about the origin of the craters. The ages were also another major concern. What was going on in terms of the age of the Moria? Young ages up to hundreds of thousands of years were considered as possibilities because nobody knew the actual impact flux. So Apollo 11 gave confirmation of the basaltic origin of the lunar Moria, that they were originated from lava flows, and also the age at about 3.7 billion years. So this was overnight a major finding and reset our thinking about the origin of the lunar Moria, or settled it in some people's minds, and the ages. Were they young or were they old? And at that same time, a geologist from Smithsonian Astrophysical Observatory, John Wood, actually took the soil samples from Apollo. Everybody's excited about the big rocks and the dates, and he looked at that and actually from the soils, from the anorthositic fragments in the soil, essentially proposed the magma ocean model and the formation of the primary crust. So this is a lesson for everybody. As we say, when you look at the NASA budget, we'd be happy with the little coins that are falling off the side of the table. Look for the soils too, okay? In addition, seismology was critically important. The astronauts deployed seismometers, which we were able to get the internal structure of the moon, a new concept, really new data for what was the inside and what it meant about the thermal history of the moon. So Apollo 12 to 17 and Luna 16, 20, and 24 really provided a diversity of understanding the diversity of the Moria volcanism, as well as the chronology and mineralogy and petrogenesis, etc. At the same time, orbital science began to give us really a documentation of the global distribution of Moria deposits and their relationship to other landforms like impact basins. And we also were able to, even starting with Lunar Orbiter 4 and 5, take a look at the distribution of volcanic features and their diversity, quite a diversity of volcanic features. And of course, with the samples in hand from the continuing Apollo missions, we were able to think about the petrogenesis. How do we link surface features and internal sources? What can we learn from the rocks about the petrology, about the petrogenesis, the generation, ascent, and eruption of these magmas? So this was followed, in fact, by concepts about the relationship of linking surface features to internal sources. And in the upper right-hand corner, you can see a diagram, a conceptual diagram from those early years in which I like to call these kind of like tree diagrams for the generation, ascent, and eruption. You got the roots down here at the bottom, and then you start coming, you got to go to the surface, so you start coming up to the surface. And you'll notice there's a lot of sketchy lines in there, which is an indication of what you don't know between source and surface. And then you've got some things going on in the near surface, which are, more or less related to pyroclastic activity, but it's not really very physically. It's boiling and acceleration, so concepts are getting down, but we're missing a huge amount there, okay? And indeed, as we take a look at the at the models that were proposed in that era, they're quite varied. And in fact, you take a look at the upper left-hand one. I've left names off of these just because I want to just give the concepts. That one shows a plume coming up to 20 kilometers, okay, and high titanium, low titanium basalts, etc. Amazing, a big Earth-like plume coming up underneath to produce this, making these shield volcanoes and all sorts of other things. On the lower part, I think this probably came from a paper that Sean Solomon and I wrote a number of years ago. But again, look at the trees, okay? You got kind of these roots down there. It's coming through the crust. It's right at the base of the crust where it's being generated. And then on the lower right, you see a multi-stage in order to understand what was inferred from the samples, the petrogenesis of stages of evolution of magma. We create in the crust a whole series of staging areas which the materials can evolve and then be erupted to the surface. So these are quite different in their configuration, and this is kind of like where we were at this time. In the post-Apollo era, 1973 to today, more or less, we have a lot of new information, huge amounts of new. We call it the lunar renaissance in a lot of ways. lunar data analysis programs. We had a bunch of missions, which were ongoing missions, which are incredibly important in characterizing the surface. And we're linking units to samples, for example, with lunar spectroscopy, in particular, Chandrayaan-1 and M-Cube. As you can see, and this and other types of deposits data really enabled us to link the samples to the surface units. And then we were able to begin to apply quantitative models to lunar processes. With GRAIL, we were able to almost like put the lunar crust in an X-ray machine and understand the distribution of mass and how surface features link to the subsurface. We had a whole bunch of new models of lunar origin that Robin Canup pointed out in a previous lecture, and of course, the discovery of lunar water by Eric Howry and Alberta Saul and their colleagues was just fundamental. It changed our complete way of thinking about the origin of evolution of magma on the moon. And then, of course, linking of Mare petrogenesis to geological processes. This is something that's happened as well. And equally importantly has been the planetary perspective. It isn't just about the moon and the Earth now. We have other planetary bodies which we can compare. We can compare the origin and evolution of magma and their origin of secondary crusts. So let's think a little bit about the evolution of the interpretation of the Moria. So there have always been, as I pointed out in those several examples, conceptual models of the origin of magma at depth and its generation from that, and then ascent and eruption. Early on, we were able to understand the effects of the lunar environment. It was obvious without an atmosphere and 1/6 gravity, we would in fact have a completely different situation than we have today on the Earth, for example. And so that led us to think about what a pyroclastic eruption would look like on the moon. It wouldn't look like a cinder cone. It would look like a pancake, if you will, because of those conditions. And it began a series of our physical understandings, applying physical volcanology to the situations on the moon. And we began to really understand what the lunar environment, how it was affecting. And we were interested in what drove pyroclastic eruptions. The moon was thought to be very dry, so water was not seemingly an option. So that was another mystery in the early days. And we slowly began to apply physical principles to generation, ascent, and eruption of the moon, a paper that Lionel and Wilson and I wrote in 1981. We started out saying, hey, you know, we can just, let's just take a good model of the generation, ascent, and eruption of magma on the Earth and apply it to the moon with these new principles of what the lunar gravity and lack of an atmosphere. And so searching through the literature in the late 1970s, we found that in fact there wasn't a good model of the generation, ascent, and eruption of magma on the Earth. So we had to do that first and then apply that to the moon. So again, physical volcanology was evolving even at that time on the Earth. So clearly, in subsequent times, we've been able to link volcanism to internal structure with GRAIL and other types of data, with thermal evolution, the seismic data, et cetera, understand its relation to thermal evolution. And again, the discovery of water in the lunar samples was a major surprise and represented huge progress in our understanding of magma emplacement. So we find too that you say, oh, well, we've come a long way, so there's nothing new, we're just refining our models. But of course, we've discovered new things and new data, old ideas, old terrain. The irregular Mare patches that Sarah Braden and her colleagues on the Lunar Reconnaissance Orbiter, Mark Robinson and colleagues, amazing things. Perhaps they're younger than 100 million years old. And then we have these ring moat dome structures discovered by Zhang at the Macau University of Science and Technology. They also look like they might be young. So how does that happen? How do we have these ideas, you know, how did we discover these things with these new data that just completely conflict with our previous ideas? This is really an exciting component of volcanism at the present time. And more recently, as we'll talk about towards the end, we're able to now link magmatic volatile evolution to the eruption. So we now know what the volatile content of the magmas is to a greater degree than before. And we can then plot that as a function of ascent and see how that maps out into the emplacement of eruptions on the surface. And we'll talk about that at the end. And again, the planetary perspective comparative planetology has helped us immensely. So let's think about what we knew about approximately about 1992 about effusive lunar volcanism. First of all, we knew that there were thousands of flows over hundreds of millions of years. The work of Hiesinger and colleagues was beginning to really show that throughout the moon. And it's concentrated in major impact basins. And so this is clear. Mare Imbrium, you can see in the upper right-hand corner, Serenitatis, Tranquillitatis. Was this a cause or was this an effect? Did the impact basin itself generate the magmas, or did they just collect them? So that was a big question. Extremely long lava flows, hundreds of kilometers long, implying very high fusion rates. This was also something we didn't think for the Earth. They're just hugely larger than what we see on the Earth. The sinuous rills implied very high fusion rates and thermal erosion. And we didn't see any major shield volcanoes like Hawaii or Mount St. Helens. Again, why weren't there any shield volcanoes if we had sustained eruptions with high fusion rates, etc.? And also calderas were missing. These imply shallow magma reservoirs, like on the summit of Kilauea and so on. But in fact, they're very rare on the moon. In fact, there's only one that I know of that one would call a caldera. There are some tip craters, but those are much smaller. And then we have these floor-fractured craters implying shallow intrusions. How does that work? Why do you have those? Where are they? What do they really mean? We also see only a few cinder and spatter cones, and of course we know that now that's related to the low gravity and the lack of an atmosphere that disperses the ejecta from these pyroclastic eruptions very widely. And then of course we wanted to know, what does the ascent and eruption of magma look like? So when we turn to these questions that we wanted to address over the decades and leading into the present, there's a huge number of them. And, the thing about Maury volcanism is it's not just an independent process. We need to link this to other geological processes. And we'll spend a lot of time talking about this today. It's not just, oh, there's a cinder cone, great, there's volcanism there. It's like, how does this relate to the overall geological environment, the thermal evolution? What's going on here? And how do these things relate to the overall processes going on the moon? Do impacts huge basins? Do they essentially uplift the mantle to get pressure release melting? And are they the cause of volcanism? Is it internal melting? What's the distribution? Why is the near side and far side so different? And so on. So all these questions here, cause us to continue our investigations over the years. What's the distribution of volcanism with space, with time? What's going on in terms of melting? What's the nature of volatiles in the interior and in the magmas? And again, what is the thermal evolution of the moon? We can tell that from Maury volcanism, and understanding the broader thermal evolution of the moon gives us predictions about what Maury volcanism ought to look like. So one of the key points here about Maury volcanism that has come from, I think, the work of Ross Taylor, who in a really interesting paper in Tectonic Physics in 1989 defined three kinds of crust, planetary crust. The first is the primary crust, which is pretty much like the anorthosity crust on the moon with a magma ocean. It's derived from the impact energy associated with the accretion and late heavy bombardment. It's a plagioclase flotation crust, like we heard in earlier lectures here. And that stabilizes and it undergoes a lot of evolution, as we learned from Mark Parmentier. But secondary crust is simply melting of the mantle, okay? It's melting of the mantle and extrusion of that out onto the surface. So you can see in the central part here, we have things like the terrestrial plumes with volcanic hotspots, vertically accreting basalt from essentially partial melting of the mantle. And of course on the Earth, seafloor spreading. And we also have tertiary crust, which Ross defined as a reworked primary and secondary crust. Now, you might think we don't have any tertiary crust on the moon, but in fact, it's quite possible that impact melts really represent, basin impact melts represent tertiary crust, where primary and secondary crust folded into an impact of huge proportions can actually create melt seas and oceans, which can differentiate to create tertiary crust. So let's think about the situation on the Earth, for example. So volcanism on the Earth is really primarily related to two factors. One of them is divergent and convergent lithospheric plate boundaries, and also things like, as you see in the upper red arrow there, the Hawaiian Emperor Seamount chain, which is essentially intraplate volcanism. So of course on the moon is a one-plate planet. So it's a global lithospheric plate that's solidified and cooled and thickened as a function of time. So it's way different than what we think about in terms of Earth's current lithospheric plate boundary and intraplate volcanism dominated secondary crust. So we started thinking about this then in a paper that Lionel and I did in 1981 and also a follow-up in 1992. We began to think more about what's going on in the special case of the moon. So we began to think about the role of diapirs and dikes. So diapir is, essentially a buoyant rise of partially molten material, potentially at depth, and then it reaches a point where you reach essentially a rheological boundary where it stalls, and brittle deformation causes the accumulated melt to propagate dikes towards the surface. So this was our configuration approximately in 1992, in which we saw differences in the crust thickness from the near side to the far side. We knew that there was a thermal evolution of the mantle of the moon, in which early on the lithosphere was thinner than the crust, but later on, as it began to become thicker, it became below the crust. So, as in the number 4 there, diapirs rising at that point would stall at a rheological boundary, whereas earlier, as at points 1 and 2, they would stall at the base of the crust. So we began to think about the role of diapirs and dikes, and the generation and ascent and eruption of magma, the role of crustal structure, the role of neutral buoyancy, for example, at 1 and 2, where the magmas are indeed denser than the crust, and thermal evolution effects, like you see here too, and then of course the relationship to surface morphology. And even at this time in 1992, we were thinking about the differences in crustal thickness. Maybe if you have all else being equal, that dikes and propagating from on the far side, not as many reach the surface than reach the surface on the thinner crust of the near side. So these are ideas that were bouncing around at that time. Since that time, we made huge progress in so many different ways. It's really, really great. So this is a list of, this list is in the reading list as are many more important references listed there on the class reading list. But, you know, we really begin to learn a lot and bring together a lot of aspects of the petrogenesis, the volatile exsolution, and linking the geology, the geophysics, the petrology, et cetera, and a more refined view of what's going on with the generation, ascent, and eruption of magma. And you can see in the bottom the irregular moray patches and ring moat dome structures, which, as we evolve our thinking, are continuing to challenge us in terms of, well, how the heck did that happen? And is volcanism still going on the surface of the moon? So let me walk you through kind of like our current understanding and what some of the challenges are for the future exploration of the moon. I'm happy to say that there are as many outstanding problems as ones we think we might have resolved or gotten a better or more clear picture of. So as you go along here, write down things that you want to do for experiments that'll be on commercial landers, that'll be on international spacecraft, that'll be in orbit, that'll be on the surface, and that find the place the astronauts should go to, in fact, really solve the problem associated with some of these outstanding points. So we're going to focus on the secondary crust on the moon, and of course that's the middle part there. And indeed, we don't see much evidence for volcanic hotspots. We don't see any evidence for seafloor spreading, of course. So it's really the left-hand part here. It's vertically accreting basalt from partial melting of the mantle. So let's take a look at the geological record, and this chart is in the Head and Wilson paper in 2017, I think. But let's talk about what the origin is. So what we see here is the potential full range of Mare volcanism, which is almost the full range of the history of the moon. So on the left-hand side here, you can see the oldest dated Mare deposits. We see a range of dated cryptomare surfaces, et cetera. So early on, we find evidence for Mare basalts in samples, as well as the end of the MG suite magmatism and other types of things that give us an idea that around 4 billion years ago, Mare volcanism started. So let's talk about the generation, ascent, and eruption. I'm not going to go into these in detail. I just want to give you pointers to go back, depending on what your interests are, to look into and explore a lot of outstanding questions. So we talk about in these papers, the 2017 bookends, if you will, rising diapirs, okay? So we've calculated what the likely size of these diapirs is. This is something to be tested. We need more theoretical assessments of the rheology of the mantle and the size of diapirs. This is an estimate, okay? So we also, if you look at the top here, you can see the accumulating melt zone, and there's a lot of questions about this as well. Here I have taken the trees and put them all the way down into the melt zone, so we still haven't resolved the problem on Earth even of the way in which mantle melts collect and then get into reservoirs and then propagate to the surface. But we're making a lot of progress here. So in this case, we work up to essentially a rheological trap, and then we know a lot about essentially how material works from the accumulating melt zone in terms of brittle deformation and propagation of dikes towards the surface. And again, you can look at we've calculated out what types of excess magma pressure is needed to exceed, essentially, to to get to the surface on the near side and the far side. These are estimates. They need to be tested. We need to sample the salts to look at their petrogenetic aspects in all these different areas. So if we press on and take a look at the factors in dike initiation and rise. So again, accumulating magma at the top. These are statements not so much of, they're statements of what we think is going on, but they're statements of like, we have problems in these different areas that need to be resolved. So I encourage you to go back to these in the papers and pick out areas in which you think you can contribute to get a more comprehensive view and essentially a holistic view. We need to talk to the petrologist, to the geophysicist, you know, essentially modeling community, and so on to really make this all a better understanding. So you have plastic host rocks at depths, you have accumulating mantle at the top of the plume, and indeed the diapir. And so then the question is, you know, how do you propagate the dike all the way to the surface? And there's lots of information in these papers about the geometry of the dike and the way in which the forces are combining to cause a variety of different sizes and scales of dikes and their rates of ascent to the surface. The other thing of it is that we see evidence for thermal evolution of the moon. So we know that this is critically important. But again, the thermal evolution of the moon that we think about has actually been challenged by the finding of Sarah Braden's paper and the IMPS and also the RMDS's. You know, if we have volcanism going on at the present time, when the elastic lithosphere or the thermal lithosphere is thought to be 800 to 1,000 kilometers thick, you know, how in the heck do you do that? That's a real challenge. Maybe our simple models are absolutely wrong. Okay, so again, this is a challenge. But early in the history, the lithospheric thickness, as you can see in number 1 there, should be less than the crustal thickness. So the rising diapir stalls at a density trap. Moving on then as the moon cools down and the lithosphere thickens to below the crust into the mantle, the lithosphere, the buoyant magmas and these diapirs will rise to a rheological trap. That rheological trap will indeed get deeper with time. And so you can see the consequences here. At some point, the volume of magma that can be propagated from a single dike emplacement event changes, okay? So in the middle 1 and 2, it can actually reach to the surface, but in 3, it actually essentially pinches off, and these dikes propagate to the surface, essentially independent of contact with the source region. So there has to be heterogenetic information that we can use to test these ideas. So again, if we think about the overall evolution of the moon, you know, we have this early Mare history when dikes might be actually connected to the surface, whereas later on they may actually be arising as isolated penny-shaped masses, dikes for sure, but again, not connected to the source region after they propagate. So let's talk about the chronology of the magmatic volcanic events in Mare history. So if we take a look at the left-hand side of the diagram here, as we mentioned before, we have evidence for Mare volcanism actually starting in the era of the large impact basins. When you think about that, you know, it's like, okay, gee, impact basins were forming at the time the Mare basalts were generated. We'll come back to the question of whether the impact basins actually initiate the effusion of the magma, there's a cause and effect there, or whether they're simple receptacles for the magma being low areas and thin crust. So first of all, let's take a look at work that Jennifer Witten has done over the last few years, in which she has documented the distribution and nature of these cryptomare deposits. Cryptomaria, in fact, you can see them in green there, and we'll come back to this diagram. So the purple is the current Mare deposits, the green is the distribution of cryptomare deposits. Well, what are cryptomaria? Basically, these things are Mare deposits that have been buried by high albedo feldspathically ejecta. So, for example, when Oriental Basin hit, Mare volcanism had already started, and you can see in the lower right-hand image of Chicard there that there's some areas of dark regions, low albedo, which are indeed Mare deposits at post-date Oriental. But it's pretty clear from the smoothness here that, in fact, the ejecta from Oriental could have covered earlier Mare. And many people have mapped dark halo craters, as you can see right here and here, that suggests that these craters are excavating below the Oriental ejecta and bringing up Mare basalts. So those are cryptomare, covered by later material. So a key point here is that Jenny was able to do is to, in fact, take a look at the characteristics of these with new data, okay, primarily things like the essentially InCube data on the Chandrayaan-1 mission, and she was able to look at the spectral characteristics of these dark halo craters that you can see in the central part here, and then look at the characteristics of them in spectral reflectance space, so to speak. And you can see here that very, very confirming evidence, not just for the composition and mineralogy, but also for the fact that these things are linked to the surface lava. So essentially, the Oriental ejecta is inserted in the middle of a phase of lunar volcanism, and she was able not to just to determine what the post deposits look like, but what the pre-deposits look like to their mineralogy as well. And you can see in her maps that the cryptomorei largely form in impact basins, okay? So there's a whole series of them here in different impact basins on the far side and on the near side. So basically, both the Maury impact basin, the Maury basins and the cryptomorei both seem to be related to impact basins. So again, it raises the question of cause and effect. So again, this is Jenny's work. It's in the reference list, etc. Let's talk about the lunar Maury themselves. This is a pioneering work of Harry Hiesinger and a series of papers culminating in a really good overview in 2011. We've had a lot of great data since that time from Kaguya spacecraft and other spacecraft, Chandrayaan, etc. And there's been a contribution from a whole host of different countries and investigators to dating these deposits. And we'll come back to the distribution of dates in a few minutes when we talk about the major factors involved in the emplacement of Maury and what this might be telling us about the mantle. But you can see from this right away, we find that some of the youngest deposits are over in the western Procolarum region, central Procolarum region, in particular that bright red unit just south of the Aristarchus Plateau dates at something of the order of about 1 billion years ago. Okay, so we're excited about the Chang'e 5 mission, which in fact will be returning samples from one of these very young units in the not too distant future, within a year or so. So the question is, how do we match the generation, ascent, and eruption theoretically and emplacement-wise, process-wise, with the observed geological record? So we've got all these things. How do we get it from the mantle to the surface? And then how do we match these with the features that we see? Here's a kind of like a cornucopia of different features associated with the lunar Maury. We have steep-sided domes, we have crater chains, we have nested sinuous rills, we have long lava flows, we have small shield volcanoes of the order of 10 to 20 kilometers in diameter, large pyroclastic deposits, linear rills with pyroclastic cones along them, floor fractured craters, and extensive pyroclastic, regional pyroclastic deposits. How are all these things related to the generation, ascent, and eruption of magma? Well, this is one of the challenges that Lionel and I tried to attack in these pair of papers in 2017. So the idea was, if magmas are delivered to the surface in molten rock fill cracks, aka dikes, and their overpressurization relationships represent a frequency distribution of characteristics of the upper part of the diapir, then we should see things propagating into the crust, close to the surface, and then actually erupt onto the surface. So we set about trying to match up the features that we see in the cornucopia of lunar morphologies, volcanic morphologies, to the basic principles of ascent and eruption of magma. So this block diagram we'll use as a basis, and this is from the paper, those two papers. And you can see here that, first of all, if we take a look at the left-hand side, there are some dikes that are just going to propagate to the middle crust, and they're not going to get to the surface. They're just going to cool and solidify. So the crust of the moon must have some proportion of the Maury basalt magmas that are essentially dikes that die at heat death, okay? So we have to keep that in mind when we're thinking about crustal densities and gravity data and so on. So the next thing is, some of them reach the shallow crust, but they don't actually penetrate to the surface. And what these do is, as shown on the lower left here, at the tip of the dike, there's a lot of gas that's being exhaled. So if they get close to the surface, but they don't come out onto the surface as an eruption, then they're going to vent gas. And sometimes this leads to fluidization of the surface and regolith, et cetera, and to a series of chains, like essentially this Mendeleev crater chain on the far side. You have to be careful about distinguishing secondary crater chains or chains related to the impact of comet, linear comet debris or whatever. But nonetheless, this is a very predictive kind of thing, and it's quite plausible that many of these features are related just to dikes that get towards the surface, but they don't actually get to the surface, and they vent gas here. So this is a great place for exploration because you might be able to get some evidence of the residual gas, and you could test that hypothesis of impact versus internal by going to the site and actually exploring it. Okay, so another thing is that the dike gets so close to the surface that actually you can see from this that it actually pushes aside the crust and results in a near-surface stress field, which yields graben. And one of the places that we see that we think this is going on is, in fact, just south of the Apollo 14 site in the Rima-Perry region. You can see on the left here that at the arrows, there's a series of cones and deposits that are obscuring the graben. And we think that's due to a configuration in which the dike almost gets to the surface, creates a stress field, drops the block down, and then some magma, gas-rich magma, comes up along the side to create these types of cones. Now, as we go further, the dikes that just penetrate the surface and extrude material out on the surface, again, there's a whole array of features that can be produced from this, but one of them is essentially small shield volcanoes. So shield volcanoes like this, if you can see on the lower right, that's, again, I think this is Tobias Meyer. It's about 20 kilometers, 10 to 20 kilometers in diameter. This is a summit pit crater. Here's the surrounding areas here. And what happens here is that you get propagation of the dike to the surface, and you get a series of essentially cooling limited flows which flow out into the surface and build up the small shield, and then essentially the eruption is over. These are probably from a single eruptive phase produced by cooling limited flows. So we have models for those as well. Again, we can test these. There are hundreds and hundreds of these on the surface of the moon, and we need to be thinking about their characteristics and how they differ from one another and what that's telling us about eruption conditions. So as we move over here to the right, we find that, in fact, in some cases, dikes will penetrate to the near surface. But again, we'll reach a point where they encounter a breccia zone, and there's a variety of reasons why at that point the dike tip may not propagate further to the surface, but rather actually propagate laterally to create a sill. And Lauren Joswiak and colleagues in a series of really, I think, excellent papers have shown the characteristics of these, following up on work by Pete Schultz in terms of the characteristics of these floor fractured craters. You can see two types: a smaller one where the central part is uplifted, and a larger one where the whole floor is uplifted, several kilometers in this case. And so Lauren and her colleagues have really tried to understand what's going on at depth with these. In the context, as you can see here, in terms of maybe a laccolith here, and indeed a sill for the larger ones. And associated with these features, you can see these all here in the red dots and green dots here, the small and large ones. These, in fact, have eruptions associated with the fractures on the floor. So these are little pyroclastic deposits. This is in the crater Alphonsus. So recently, Lyle and I published a paper where we tried to understand the intrusion of the magma into these deposits, into these brecciated crater floors, and what might happen as a function of time. So I'm not going to bore you with all the details here, but I refer you to this paper and just to think about three things. First, you have a dike formation, dike emplacement event, stalling of the sill of the dike, and then propagation laterally to create a sill. And then as a continuum part of that, okay, the next thing that happens is, in fact, you have essentially the sill formation and uplift. And indeed, part of that is you get volatile accumulation into a foam layer. So the topography of the floor fractured crater differs as a function of time. It isn't just going up. In fact, it goes up due to these factors, but at the end, due to cooling, it also comes down as it solidifies. So we've calculated what the theoretical predictions ought to be for this, which we can test with more detailed investigations. I'd love to go, for example, to the crater Humboldt and do regional geophysics and geology on a crater like this. It'd be a great thing to do. There's many questions that we need to ask in relationship to individual vents and other types of features associated with here. So in the final analysis, the sill cools, undergoes final solidification, and decreases in thickness, and so the floor tends to go down. This can also be a time when the floor can crack, and some of this foam prior to its solidification can indeed be extruded out, as we see here, to produce these pyroclastic deposits. So lots of predictions here, lots of background work, lots of work to do in understanding what's going on these. And of course, the last couple have to do with when the dike actually overshoots the surface and we get very high effusion rate flows and sinuous rills. I refer you to the paper of Deborah Hurwitz and colleagues who have mapped out all the sinuous rills on the moon and talked about their characteristics and morphology. It's a really excellent paper to start if you're interested in this. So what happens when we get overshooting the surface and very high effusion rates? Well, the first thing we do potentially is to get the propagation of the gas out onto the surface. So in the case here, the gas vents to the surface. You can see the gas is at the top of the dike, and then as the magma comes up, it's also undergoing decrease in pressure, so it also is generating gas. So the first phase is the dike tip hits the surface, and you get essentially penetrates to the surface, and you get extrusion of lava out on the surface to produce regional pyroclastic deposits. And these things are all over the place. I mean, they're quite extensive. So the question is, how does all this fit into a normal volcanic eruption? So we need to think about that. And then, of course, when we see that it overshoots the surface, we also get a series of lava flow types. So huge lava flows, like the ones we see in Imbrium, shown in the lower right-hand corner here, hundreds of kilometers long, many hundreds of kilometers long. These are, in fact, likely to be potentially volume-limited flows. At least you can imagine a situation in which, as the magma is coming out, it's limited by the volume of magma in the dike. So as the dike closes, essentially it stops advancing simply because there's no more magma to, in fact, extrude out on the surface. So these are volume-limited flows. There's also the case, of course, of cooling-limited flows. If you look in the lower left-hand corner here, imagine a flow coming out. Okay, indeed, it's starting to cool here, and essentially it shuts down in terms of lateral advance, forward advance, but the magma is still coming out because it's a cooling-limited flow. And indeed, what happens then is that the levees are breached, and you get situations like this, where we have a whole series of flows, and this indeed gives us rise to compound flow fields. And you can see here, too, probably volume-limited flows, and then a whole bunch of features in here that are really dead ringers for terrestrial examples of compound flow fields where, in fact, it's cooling limited flows. So we're currently working on the theory of these two types of flows and how we might distinguish them, and using these basic measurements as examples. So, of course, we've had a lot of progress about, particularly with the work of Eric Howry and Alberto Sol and their colleagues, in terms of, and Mac Rutherford, in terms of how molten rock is rising, but most importantly, how the volatiles are operating in the context of the evolution of the emplacement of the material. So there's a really, I think, important paper by Mac, Alberto, and Eric and colleagues in American Mineralogists, which is a model for the origin, ascent, and eruption of basaltic magmas, particularly the picritic magmas. So what this does, as you can see on this box here, it talks about volatile generation as a function of depth. Okay, from 550 to 50 kilometers, from 50 kilometers to 500 meters, and less than 450 meters. There's real major differences there, okay? So what we end up seeing here is that the volatile generation, and that's not just exsolution, it's, smelting reactions as well as exsolution, leads to, in fact, magma fragmentation and quite a diversity, but the predictions from this model are really, really important because it's basically a synthesis of what's going on in terms of volatile generation and potential for magma fragmentation as a function of depth. So if you can imagine a single dike coming up from the depth, we can take this information from the Rutherford et al. Paper, and as Lionel and I have tried to do here, is to convert that into an understanding of what's going on with the lunar basalt volcanic eruption structure and morphology, what the gas release patterns do in terms of sequential eruption phases. So that's in a paper we published this year in GRL, and let me just talk a little bit about that. This is something that provides a whole series of predictions, which may or may not be right, but basically it's the best we have at this present time, bringing together what Mac Rutherford and his colleagues have done in understanding the ascent and formation of gas and emplacement of that as a function of depth, and then converting that into an understanding of what's going on with lava flows. So let me walk you through this briefly. Think about these not as, oh, this is the way it is. Think about these as predictions that can be tested. We talked before about pyroclastic activity and dark mantle deposits, but we couldn't put them in a sequence for what's going on with a lava flow. In this, using the data from Mack and his colleagues, we're actually able to do that now. But these are models, they're predictive, and they can be tested. So think of where you can go to test these various models. So let's start with the left-hand box here. And you can see here what we've been able to do is to outline a whole series of characteristics. 4 phases of the eruption, what the dike configuration is at that point in relation to the crust and mantle, what the surface predicted eruption style looks like, what magma rise speed looks like, the volume flux, the percent of the dike erupted. You can see it starts out slow, goes gangbusters here, and then tends to trail off. The duration of the phase, we've estimated these from theory. And we've also taken a look at the flow advance speed, flow advance distance, and the vesicularity of the lava leaving the vent. And you can see they vary to 0 vesicularity to very high. So these are predictions which we can indeed test. So if we take a look at the first one here in phase 1, this is the dike just penetrating to the surface, as you can see here. And what happens, and I'll just go through this in the next slide here, it penetrates to the surface. We get a transient gas cloud phase, and then we get essentially a pyroclastic mantle, a thin pyroclastic mantle that's very widely dispersed. So we see a lot of these very widely dispersed mantles. Let's try to match these up with the lava flows that they might have been generated from. The second one is the dike base is still rising, okay? There's a high flux because this is the major part of the dike, okay, 70% of the dike. And this initiates an Hawaiian eruptive phase, which in fact is getting rid of a lot of gas as the magma is coming out. And it indeed is about 70% of the magma comes out at this point. And if you take a look, you're predicting here that we're actually getting a very, very large optically dense plume in the interior part and an optically underdense portion of the plume in the exterior. And this results in a variety of cooling behaviors for the pyroclastics. So in principle, we should be able to take this model and pick up pyroclastic at certain places on the moon and actually calculate the distance back to the vent from this kind of theory. So this would be great in future exploration if we could get samples from all over the moon and try to place them back, the glass beads, into the essentially locations of the lava flows from which they were derived. The third phase is the dike equilibration phase. So essentially, most of the mass has come out, most of the volume has come out, and so this is a lower flux Hawaiian to Strombolian transition phase. It slows down, and when it slows down, that means that the magma spends longer in the upper part of the dike. More gas exsolution can take place, and you'll see what happens is you get a lot of gas exsolution and rise, and this takes us into a Strombolian phase. So this is the Hawaiian to Strombolian transition phase. So this is really important too because this is the beginning of huge amounts of volatiles coming out and very vesicle-rich magma being extruded out onto the surface. The final phase 4 is the dike closing phase. Okay, so obviously to penetrate this dike to the surface, the elastic forces have to push the crust aside, and indeed it's the overpressurization that's keeping the dike open, but with time the elastic forces will relax and we will in fact close the dike. Okay, so that means in this stage it's really interesting because the dike is spending a lot of time in the shallow part of the crust. It's exsolving a lot of volatiles, any of the residual volatiles, and then in that upper part of the dike, as the dike closes, that very vesicular material is being extruded out onto the surface. So this is a prediction for the late stage eruption that should look something like this. We should actually get proximal magmatic foam-rich flows that are extruded through cracks. We also should get very vesicular magmas injected into still molten lava flows. So if we have in phase 3 a big lava flow coming out, this is entirely plausible that this late stage magma will be actually intruded into this deposit and this active flow to inflate it. So this is another thing we should be looking for too. And there's a variety of missions being proposed to examine the vertical structure of lavas. Moondiver by Laura Kerber and others. It's one of the kinds of things we really like to look at the vertical structure to be able to distinguish these things. So let's look at the evolution of interpretation. And so we've gone from conceptual models of the origin of magma at depth to beginning understanding what's going on in the lunar environment, what drives pyroclastic eruptions, how we can apply these physical principles to the ascent and eruption of magma on the moon. We've been linking things to the internal structure, the thermal evolution, and again, the discovery of water was a major, major factor. And again, let me emphasize, new discoveries challenge our old ideas. When we look at the irregular Maury patches and the RMDSs, it's like, what's going on there? Sarah Braden and her colleagues listed here, a really excellent paper, beautiful documentation of these things, amazing. 70 small topo anomalies, less than 5 kilometers in diameter. The crater size frequency distribution of these features, in fact, suggests that they're less than 100 million years old. How do you do that? How do you have 100 million year old active volcanism when we think that the thermal evolution suggests that the interior generation of magma shut down, over 1 billion years ago? So this is a challenge, and here's one of the largest ones, the Ina feature. It's like, okay, you got to get your head screwed on right here because these are little mounds. They're like little meniscus type features, like mercury you poured on the surface. Totally bizarre, and indeed they just look young. They look extruded out like yesterday. Okay, here's a perspective view of this floor of Ina. You also have this rough material on the floor. All of these things, as Braden and her colleagues showed, give ages of less than 100 million years. And so, how do we do that? What's going on here? Here's the colored topography. You can see these are tens of meters high. There's a depression in the middle. Lots of information here, and a real challenge to our understanding. So, if we think about lunar Maury volcanism, crater distributions from these IMPs suggest that ages of 100 million years, less than 100 million years. Here's the Hiesinger et al. Distribution of what we see on the surface. Here's 100 million years at this arrow. I mean, this is amazing. This places strong constraints on models of the moon's thermal evolution, if in fact these are this young. So this is a great exploration target. I would love to go and land inside Ina and have a month there to, in fact, explore around to really try to understand the structure, morphology, and ages of these features. So this would put volcanism basically up to the present, which again is a challenge for our models. So Feng Zhang at Macau University of Science and Technology also reported recently something Pete Schultz had noted decades ago, but I completely missed these things. One of my jobs in Apollo was to look at landing sites on the lunar Moria. I can't tell you how many craters I looked at. I never saw these things. Partly that's because of the illumination geometry, but of course Pete saw them, and they've been kind of like documented in these new data. So here's a picture of the Moria. We see impact craters because the illumination is coming from the left, so these are depressions. But take a look at all these other features here. There are a bunch of little mounds there that have moats around them. These are amazing. But where do they come from? And if you take a look in detail, you can see here, there's one of them, okay? Some of them look like they extrude down into pre-existing craters. One idea is that these, again, are really young. They have seemingly smaller numbers of craters on them, and they intrude into things that Sasha Basilewski has dated from crater degradation to, in fact, very recent ages. So could RMDSs be evidence of very young volcanism as well? This is really amazing. We don't know. We need to land on these things. We need to sample them. We need to explore them. We need to understand the processes engaged here. So let's lurch towards a close here by talking about the chronology of Maury basalt emplacement. So we have Harry Hiesinger and his colleagues' data in the synthesis paper in 2011. And part of the questions we have to do with, in fact, why is there a near-side, far-side asymmetry in the distribution of Maury lavas? We know that's the case. You just have to look at this map alone to see that. Where is the earliest Maury basalt volcanism? Where is the latest Maury basalt volcanism? Is there a near-side, far-side asymmetry in age distribution? We certainly see it in terms of volume, but is there an age distribution difference? What's the role of the Procolarum creep terrain? That's this area shown in black here. And in fact, what's the role of basin formation and crustal thickness? And what can this all tell us about the mantle source regions, which is really what we want to get at in the final analysis. So let's take a look first at the chronology of basaltic eruptions. And again, we have the cryptomaury and the Maury, and we point out that these things, as Jenny Whitten has pointed out, are really very closely related to impact basins. You can see them all here. So Jenny did another analysis in which she asked the question, how is Maury volcanism related to impact basins? Is it active or passive? What she did was she took a look at the Oriental Basin and looked at the post-Oriental Basin volcanism. If Oriental, in fact, a huge basin, caused uplift of the geotherms, maybe mantle convection processes, then we should expect to see volcanism centered very closely to, in fact, in time to the distribution of the Maury basalts, in the interior and portions of Oriental. If it's not related to it, we should expect to see these things start later and extend for longer periods of time. So Jenny dated all these and used M-cube data to look at the mineralogy, et cetera. And I'm just going to present a summary here. Again, the Oriental Impact Basin event is what we're looking at here. You can see the ejecta makes up about a hemisphere of the moon. We're going to be looking into the interior, and 1 second that passes will be 100 million years, so fasten your seatbelts. So 1 second is 1,000 million years. The Oriental impact is the start. Quite a bit later, tens of millions of years later, we get the interior Moria, and you can see that the Moria actually go on for quite a long period of time. This is not something that happened as a result of the initial basin formation here, okay? So Jenny's data, wait, there's more coming up here in a picosecond. It comes all the way out here to, don't hold your breath, but we're not going to wait. There's one more. There, 166, okay. Okay, so here's a summary of Jenny's data here, okay? If we look at the distribution of Oriental ages shown in yellow on the right, then they span quite a bit of time, from about 3.7 billion years ago to about 1.5. So they're clustered at the time of major Mare volcanism, but not associated with the impact event itself. So what she showed was that on the margins of the sides of the moon, if you will, the limb of the moon, from near side to far side, from thick crust to thin crust, Oriental had about the same distribution of ages, that is, over this period here, but the abundances, in fact, were much, much less. So again, this says that there is melting going on in the interior, much like it is on the near side, but it's just less magma coming out. So let's ask the question here, why is there a near side? Let's take a look at some of these other major questions here. And we can do this by looking at the distribution, like the earliest, latest Mare volcanism, the asymmetry and age distribution, the role of the PKT, et cetera. By looking at the distribution of these things, I'm going to show you this movie here, and you'll hear a couple of things. So first of all, we slowed it down a bit. So 2 seconds is 100 million years. When you hear a beep, there will be Mare volcanic unit in place. This is a synthesis of all the dates that I've been able to put together. And the dots that you can see here, like this blue dot, will show the location of where that volcanism is. The dots are color-coded by age, scale at the bottom, so you can see, don't touch that, you can see here, basically, each color is decreasing by 500 million years, 500 million years as we go towards the present. We can also see that the red lines indicate the near side and the far side, so between these two red lines is the near side, and the other part is the far side. And essentially, the area here is the Procolarum Creek terrain, and indeed, the map color scale is in Grail-derived crustal thickness, where you go from 67 kilometers down to less than 20 kilometers in these areas here. So let's take a look at this, keeping those questions in mind. Where is the oldest Mare basalt? Where is the youngest Mare basalt? Is there a near side, far side distribution difference, et cetera, et cetera? Okay, so with any luck here, okay, you can see that it started in the eastern part of the near side and has now increased to broader scale areas here, okay? And the other thing you can see is that the near side and the far side, okay, there's less on the far side, but each time you get something on the near side, you also get something on the far side. It's just not as much. So again, even down here to where we are in about 2.9, you're seeing near side and far side lavas. Now it's obviously slowing down. This is the 1.5 to 1.1. You're still getting these on the far side, even at this young age. And now we wait. So this is what people think the tail off in volcanism is all about. But indeed, we're still waiting here. We're down to 0.3 gigayears, 0.2. Okay, there's one of those three dots are the irregular Mare patches that have been dated. And so again, this is really exciting because perhaps they mean that, in fact, there's volcanism that's actually going on today. So let's think about this and kind of like ask again these major questions about Mare basalt distribution and chronology. Why is there a near side, far side asymmetry? Well, we've seen from Jenny Witten's work and others' work and the dates and the movie that in fact there is far-side Mare volcanism, and like Jenny's Oriental sequence, basically you get pretty much, except for the last 100 million years, you get pretty much similar occurrences on the near side and far side throughout. It's just simply that the far side has fewer eruptions and fewer volumes of lower volume of volcanism. So again, it seems to correlate, as you can see here, perhaps with crustal thickness. So is the question, is the crustal thickness the key factor? Could it be that, again, it's very simple and it's just crustal thickness variations that are causing a near side, far side asymmetry? This has huge implications because, of course, if it's the Procolarum creek terrain or other factors, this means that the mantle is extremely heterogeneous in a near side, far side sense, and the source regions are very, very different from one another. So this is not a trivial question. The findings that Lionel and I have reported would argue that it could easily be crustal thickness that's causing the main difference in this. But again, that's a testable hypothesis. One of the key points that we will be looking at with a Chang'e 5 sample return mission from the young deposits is, in fact, what is the nature and petrogenesis, age, and mineralogy of and major element composition of these deposits, because in fact it's going to come from the Procolarum creek terrain and it's going to be really young. So where's the latest volcanism? It's clearly in the northwest near side. Is there a near side, far side asymmetry and age distribution? Slightly, but really, not very much. Okay, so it's mostly in the young end, but still there's far side basalts that are in the 1 to 2 billion year old time scale. What's the role of the Procolarum creek terrain? There's lots of literature on this, and this is a critically important point. Mark Ozoric and Roger Phillips and others have argued that the Procolarum creek terrain is the reason that the Mare basalts are so important and so young there. Perhaps that's the case, but if you look at the crustal thickness map, it's also an area of pretty thin crust. And so this is an area we need to continue to discuss. The Chang'e 5 data will in fact help us to really understand that. What's the nature, rate, and fate of volatile exsolution? Again, these are really critically important points. This is why future exploration, exploring and bringing back samples of all these different units is really critically important. My dream is that the commercial capabilities that we're looking at evolving now will be able to duplicate what the Soviets did 40 years ago with the Luna sample return missions and be able to essentially return samples with very low cost back to laboratories on the Earth so we can get to full geochemical analyses and age dating, et cetera. So that's another thing. We really need to think about how to develop these capabilities, what instruments to put on, and how to make sample return from the moon essentially not an unusual circumstance, and certainly not 40 years between missions. So again, this is really critically important, and what we all want to drive for is, in Mare volcanism, is how to understand the mantle source regions. What is going on? Are these diapirs correct? How are these diapirs initiated? How do we go from what Mark Parmentier told us about the formation of the magma ocean and the aftermath of that in terms of instabilities associated with residues of the lunar anorthositic crust, and what that might have done to initiate overturn and indeed the descent and then ascent of diapirs to create Mare basalts. This is a major area that we don't know much about at all, and a source of really important issues and questions, many of which can be resolved by future missions. So what are the questions that we need to address? How does the lunar crust form and evolve? Well, we made tremendous progress on that if you compare what I'm saying now to the earlier slides about the pre-Apollo era. When and where does mantle melting occur? That's critically important as well. We thought at one time early on that, it was very simple. Apollo 11 basalts were titanium rich. Apollo 12 basalts were not titanium rich, and so therefore it was a trend of melting with time. And then, of course, the remote sensing people came in and said, but wait, there are young, high titanium basalts in the west. We still don't have an understanding of when and where does mantle melting occur. This is a critical area of investigation. What's the style of mantle melting as well? The diapir idea is based on firm physical principles, but how does the magma collect? What initiates the diapir? And what is their diversity in terms of the aftermath of the magma ocean hypothesis, in which overturn might have produced different materials in different descending diapiers, and then subsequently in ascending diapiers. What's the evidence for petrogenetic diversity? What's the total amount of volcanism that's occurred? Do we know really what's going on in terms of dikes, et cetera? There have been papers from the Grail team which have strongly suggested that there might be some anomalies in the central part of the moon that might be related to volcanism, and estimates have varied widely from about 10 to the 7th cubic kilometers to quite a bit more than that, depending on how you count what might be the buried deposit. This really needs to be investigated in detail. And again, we need to know something about the flux. What's the distribution of volcanism with time? And it isn't just so much a curve, it's like how much comes out in individual events as well. If you think about one lava flow, if you think about the mean flux of volcanism from the moon, is very low, okay? And about 50,000 years of the mean flux is what comes out in a single eruptive event. So this is something we need to understand much better as well. What about mantle melting in space and time, and what's the nature of volatiles in the interior and in the magmas? And again, how is this all related to other processes? We're coming now to the point where we can do very, very important quantitative models of impact basin formation, of crater formation, the thermal evolution of the moon, generation, ascent, and eruption of magma. In the next decade or so, we'll be bringing these things together, getting new samples to test these ideas, and putting together in an overall view of the thermal evolution of the moon. So I hope that's been useful, and now we can turn it over to Ariel Deutsch for questions. She's going to answer them.
Thanks, Jim. So our first couple questions are about crustal formation. Is it widely accepted that the plagioclase crust was a global layer before Mare volcanism?
I think so. So yes, I think that's the case. That's generally the widely accepted interpretation. Of course, because if you have a global melting of that the plagioclase flotation crust, certainly from a mineralogical point of view, it's extremely widespread, and there are no places where we think there's no crust in the exposed surface. The key question is, what do the impact basins do? For example, if you look at Mare Imbrium, for example, then you can see that in this particular area here that it's covered with lavas, and they're kilometers thick. So could the impact basin have essentially stripped off the crust to the level that it's actually exposed mantle on the floor of this that the lavas have covered up? But in general, I think it's certainly thought by most to be a globally continuous crust.
Does volcanism have a role in tertiary crust?
Yes, so the question, does volcanism have a role in tertiary crust? Absolutely. One thing I didn't talk about, because this was lunar maria per se, was in fact the what are known as the red spots. Classically, they have a downturn in the ultraviolet in their spectral characteristics. Indeed, diviner data from LRO has shown that they're silica rich. So we've suspected that for a long period of time. Domes like the Gruithuisen domes are very, very good candidates for, they're certainly volcanic in nature, and something that Brad Jolliffe and colleagues have talked about on the far side of the moon maybe represent even explosive eruptions. So the question is, where do those come from? They're very evolved magmas. They're very silica rich, both from the diviner data as well as the morphology. And so could these be, in fact, tertiary crust, that is, reworked primary and secondary crust? Could there be intrusions at the base of the crust that have mobilized material or even been large enough to have differentiation occur to produce these more evolved magmas? So I think that's one component of potential tertiary crust. The second component has to do with the idea that, well, impact melts. So work by Will Vaughn and other colleagues have shown that many of these, like Oriental, they're impact melt oceans and seas. It's debated about whether they actually differentiated or not. Very major question. It's another place to send missions to the floor of Oriental to do samples on this impact melt deposits and the ejecta from craters on that. Because this is another way you can get tertiary crust. Reworking of primary crust and even more basalt, mixing them together to produce tertiary crust in the form of impact melt seas.
A few questions about dike propagation. So the first is, if you could explain how the viscosity of magma influences whether a dike can reach the surface or not.
That's a good question. So, let's do in members there. If we think about a basaltic magma, generally the temperatures of the basaltic magma at depth are sufficient so that the details of the composition, broadly speaking, basaltic, generally basalt, it's not very critical at those depths. So the basaltic emplacement, the viscosity is probably not going to change very much. On the other hand, if you have this partial melting, like we talked about in the Cretaceous domes, it's going to have a huge effect because these magmas are extremely viscous, and so the dike characteristics are definitely influenced. And Lionel and I did a paper in 2000, umpty dump, I don't know what it was, but maybe 13, I don't know, somewhere back then, in which we looked at the generation and ascent of these magmas from a theoretical point of view. So the dikes are quite large, and they're very viscous, and indeed, explosive eruptions could occur. But generally, from what we know about the range of compositions of basaltic magmas on the moon, the viscosity of them in the basaltic dikes is probably not very much of an effect. It's probably not very variable, so not very much of an effect.
You spoke about how the ascent of dikes is influenced by the location of the rheological trap. Is the rheological trap something we can see with Braille data?
So the rheological trap, it's a mental construct, okay, in the sense of essentially the elastic lithosphere. Okay, there's a thermal lithosphere. So if you think about the broad definition, there's probably 15 different kinds of lithospheres, but I think it's just a simple model of a thermal lithosphere where you define that as the point at which partial melting begins, for example, or it can be defined as the point at which the crust stop, the lithosphere, the layer on the moon changes its physical properties, so it's much more brittle, for example. Those are conflated statements, but basically, with time, essentially the moon is cooling off, so that the temperature, the isotherm associated with the definition of a lithosphere is going to descend with time. Early on, Sean and I showed in a 1980 paper, maybe, looking at the flexural responses of the Mare basins, we showed that the lithosphere was probably much more variable early on, and then it evened out with time, as you might expect a thermal structure to do on a globe. So we can't really see it with Grail because it's constantly changing. The seismic, so it's not a static thing, it's a dynamic thing. The seismic data suggested that the base of the thermal lithosphere was about 800 to 1,000 kilometers depth. You would probably, the way you might see something with subsurface detection might be where you might see that at a certain time, a lot of diapirs rose, and they were trapped at a particular time in which the residues of the diapirs might be able to be detected probably much more by seismic data than with Grail data. So it's one of those things about understanding the thermal evolution of the moon and working together with geophysicists. And again, please keep in mind, we'll see on Mars in a not too distant future, at the end of November, the importance of seismic data, okay? So we need a seismic network on the moon. The more detail we can have that, the more we can actually look at the structure of the upper mantle and try to see something like this. But actually catching it in the act, it would be a very difficult thing to do. It would be impossible, I think.
So you have a lot of experience combining both the observations and geophysical models, using models to test observations and using observations to inform the models. Can you speak a little bit about how the state of the field is right now and how the models and the observations that we have agree?
Sure. I would say that depends on the subdiscipline, if you will. So, for example, if we take impact cratering, essentially the kinds of models that have been pioneered by a number of people, including Jay Malash and Brandon Johnson, many others, have really become sophisticated. So they actually are mapping out and are able to track particles and the temperatures of particles with really good physical estimates of the characteristics of the materials themselves, so how they behave under a variety of shock processes and thermal processes. So this is becoming really, really important, okay, and very, very predictive. So that's an area that one should work very closely, hand in hand, geologists and geophysicists who are doing the modeling to test these predictions. Okay, so this is great because it's the paradigm for then going in and actually being able to make a prediction and go test it with one mission, with a dozen missions, with going back to the lunar sample collection, and saying, so that's what that was about. So I would say basin and crater formation is really important. How much energy goes into melting? What's the depth of sampling and excavation? All of these things are critically important. And again, having the geological interpretation and working with these people, back and forth between geologists and modelers is critically important. We find that really is important as we've been working on the early climate history of Mars and also with the volcanism and impacts on the moon, et cetera. Volcanism is another one. I hope I've been able to show you today that we've learned a lot since the time we didn't know whether these large craters on the moon were volcanic or impact origin. But where we are now is with some good models that are really testable. So the model in the GRL paper that I shared with you about the matching up the volatiles with the volatile evolution that Mac Rutherford's paper outlines with the geology that the GRL paper that Lana and I did is a predictive one. That's for a certain set of conditions. So we need to explore that parameter space. We need to go and look at the vertical structure of Mare basalts and crater rims and pit craters, et cetera. We need to sample along these lava flows. Wouldn't it be great to get a rover to go along the lava flow with a GPR and sampling devices, et cetera, to be able to actually look at the lateral and along flow and across flow variations in the volatile content, et cetera, et cetera. Where do these things come from? We make theoretical predictions. We've been flummoxed by these irregular Mare patches. Are they young? Are they old? By these ring mold dome structures, those are observations. Theory needs to come up to provide models for that, okay, which we can test. Again, we have a model for that. We've done some work. Liu Chao and others have suggested that these might be magmatic foams coming out from degassing of the interior and actually be ancient in age. Is that the case? Well, we can go take a look, bring back samples, do remote observations, test it. Just landing on one of those things alone, what is the structure of these things would be really important. So there's lots to do in terms of working the theoretical predictions as well as the observations. And again, each new observation helps us to focus and improve the theoretical models. So they're models, okay? But it's a process that really helps us to understand what's going on.
A few questions about young volcanism. The first is, why aren't there RMDs homogeneously distributed across the Mare? And what does that suggest about the lunar volcanic history?
So that's a good question. The RMDSs, why aren't they uniformly distributed across the Mare? They're not, actually. Part of the problem in doing the census for these things, we just submitted a paper to JGR, on the global distribution. Part of the problem is we have to have certain illumination geometries to actually detect these things. It has to be low enough solar illumination so that basically you're looking, you can see detect these mounds. So we don't have a global view, but it's clear there's many places where they are, but also many places where they're not. And so how do we account for that? That's a good question. As we think about models for the evolution of lava flows, one of the ways in which we might get these RMDSs is in that stage 4 that I was describing of the lava flow emplacements. If you inject foamed magma, that is volatile-rich magma, into a lava flow that just came out and then inflate it, the evolution of that could easily lead to second boiling, production of magmatic foams in the flow, and localized production of RMDSs. So that's one possible model. And that would not be typically across the whole Mare. It would only occur in certain parts of these lava flows. So that's one example of how the RMDSs might be formed. But it's just one example. We need all the help we can get to try to figure out what these things mean. Are they young? Are they contemporaneous with the flow? Why is there a moat? Why is there a mound? What the heck's going on there? That just challenges a lot of our views.
If volcanism occurred or has occurred in the last 100 million years or so, what's going on in the lunar interior to allow this type of activity?
That's a really good question, and I think that's the I don't know what the that's the big question. Okay. Um, uh, in a previous paper on INA, Pete Schultz argued that there was late-stage gas venting, and that actually blew a lot of the regolith out and made the surface look immature. He was arguing that there were some residual effects from big basins and things like this, as I remember, which caused late-stage volatiles to be erupted out onto the surface to create these features. Even that is hard to do. You know, one thing about INA is that it's a pit crater sitting on top of a shield volcano. The shield volcano has been dated. It's about 3.5 billion years old. If you were to have magma coming out of the surface and erupting onto the surface, why would it wait 3.5 billion years in a very specific place at the top of a shield volcano? That's a tough one. There's only a few of these that are related to shield volcanoes. A lot of them are just in the middle of the mare, the imps themselves. But you know, these are the kind of questions that we have that we have to we have to explore, continue to explore.
So you mentioned Chaulet's work on the imps and the hypothesis that they may represent ancient magmatic foams. Can you describe a little bit about what it would be like to actually hold a cooled magmatic foam in your hand?
Sure. Cool. Thanks. It's cool. Actually,
or hot.
A hot one wouldn't be so bad either because essentially, yeah. Anyway, they cool down pretty quickly. So it's pretty much like pumice. Okay. So magmatic foams are in excess of 70%, essentially pore space, if you will. So it would basically be like a piece of pumice, except it would be basaltic in nature. And we think that in Chow model, we think that basically what's going on is that the INA might be a pit crater on top of this volcano. And again, as we were talking about in the 4 stages of mare evolution, the 4th stage in which you have the magma decreasing in its ascent rate, so it's slowing down, but you're squeezing it out, that could be really important because if the magma is sitting there for a longer period of time, it's exsolving all the rest of the volatiles, so it should be very bubble rich. If you're in a pit crater on the summit of a volcano, you're cooling a boundary layer, that's the floor of the pit crater, and if you're then extruding, you're degassing all this magma, you could create a subsurface foam below the layer, and as the dike closed, it could push up to form that and essentially have these magmatic foams extrude out on the surface. You know, there are problems with that. I mean, Mark Robinson has pointed out, wait, there are boulders on the surface. How can you have boulders on the surface of a foam? You know, some foams are really strong. Styrofoam, for example. Why did they put it? You know, it's something that keeps things from being crushed because it's essentially very strong. So, you know, all of these questions are things that are subject of current research. For example, we've been looking at the nature of impact craters. Some of these craters look like small pit craters on the surface of many of these mounds. Could that be due to the characteristics of the substrate? We've done some calculations which suggest that impacts into a magmatic foam, the energy partitioning is totally different than it is in a basalt. And if you think of a vertical impact in a magmatic foam, the energy partitioning is not into fracturing, breaking, and ejection. It's into vertical crushing of pores. And so it creates a deep pit that's narrow, and that's very different than what you would get with a normal basaltic lava. So again, these are predictions. We can go back and look at the data, look at the images, and try to distinguish among them.
And lastly, a couple of questions about volatiles. The first is, are there any volatile release phenomenon that are associated with high effusive lava flows along the flowing process? So in other words, they say, can we observe volatile release phenomenon along individual lava flows?
Yeah, the answer is yes. And in the older models, you know, like I was saying earlier, that we basically were just dealing with the magma coming out and extruding, et cetera. But now with Rutherford et al. Paper, we've tried to put together this GRL paper as a general view. So yeah, absolutely. So you know, one of the things, the key is the relationship of the extrusion rate and degassing, where the degassing takes place. for example, if you, in the early stages of the eruptions, when you have these huge pyroclastic eruptions, as on the Earth, a huge percentage of the volatiles are just essentially being released in the pyroclastic eruptions. And yet, as the eruption process slows down, and then you start extruding lava out to the surface as well, you end up carrying a lot of the exhaled volatiles into the flow itself. And so that has very strong implications for what happens on the moon. You know, it's quite possible that the upper parts of the lava flows actually are more like a magmatic foam in some parts of the lava flows. So then, of course, as the flow is going along as well, it's exhaling gas even before it might become inflated, and that gas solution, depending on where you are and the rates, et cetera, is going to produce a lot of vesiculation. So we know in the vertical cross sections of lava flows that vesicle distributions in the central parts of the flows between the cooling thermal boundary layers can be quite substantial, and sometimes you even get pipes of vesicles coming up through the remaining magma. All of these things are certainly possible in these lunar flows as well, and they're all exacerbated by the low overburden pressure and the low atmospheric pressure as well. So we're just finishing up on a paper essentially trying to map out the details of the individual flows like we talked about in the GRL paper, but really a much more detailed model of the flow, trying to predict what the vertical structure will be. So again, these will hopefully be useful for testing these ideas when we can get to rappelling down the side of a pit grater, for example, as Laura Kerber is leading up an investigation to try to do for the Moondiver mission.
Okay, and lastly, here's a fun question. Based on Alberto's detection of water in lunar samples, can we expect alteration minerals to have formed on the primary lunar crust in a supercritical steam atmosphere? Also, why don't we see alteration via impact-generated hydrothermal systems on the moon?
Okay, so it's a really good question. So to a first order, if you think about the crust, okay, of the moon, you know, you probably are not getting enough liquid water in place in the crust or even on the crust to actually sit around long enough to cause alterations. So remember, on the surface is a vacuum, so you need to get water deposited on the surface. You know, of course, I'm talking about in the equatorial regions. You know, primary formation of water from these things, it's not going to stick around very long. And indeed, you know, it's not going to be mixed into the crust in a lot of detail such that you might expect a long-term aqueous alteration. So there's no groundwater system per se. You might get contact relationships. We should be looking at these things. You know, there's the rusty rocks from several of the Apollo missions. Could they be relations like this? Many people thought they were contamination, but maybe not. Okay. Again, keep in mind that we have a very small percentage of the surface that's been sampled. So, quite frankly, nothing would surprise me in that context. I think, you know, we make some predictions in these papers about where the water goes and how much there is. I've been unable to come up with a business model for investing in hydrothermal alteration minerals on the moon. Okay, I'll let you know if I do and sell you some stock. But I think probably it's minimal, but it can tell us a lot. So we should definitely be looking for it.
Thanks, Jim. That's all the questions we have.
Okay, thank you very much. Let me go to the last slide here. So next week, October 31st, we have lunar impact cratering and formation of impact basins. This is a really great lead-in. We can talk about some of the patterns of deformation and associated with these big impact basins that are essentially the receptacles for the lunar maria. And Oz Osensky from the University of Western Ontario and Brandon Johnson from Brown will be giving that lecture. And it's really going to be great because, you know, this is exactly what some of you were asking questions about the relationship between observations and modeling. And Oz has been doing great stuff in terms of the observations of terrestrial impact craters, particularly Canadian impact craters, and leading a host of Canadian astronauts into the field in Canada to teach them all about the field geology of these things. And Brandon has done really great modeling of impact basins primarily, calling on GRAIL data and ISAIL codes and other aspects to really get an idea of what the predictions are and how the distribution of ejecta and other things should behave on the moon. So this is a great opportunity to tune in and listen to them and learn a lot about how you take these two data sets and come up with a very synergistic understanding. So let me point out too, just for the future, that on November 7th, NASA Administrator Jim Bridenstine will be talking to us about Space Directive number 1, and we're really anxious to hear that. And then again, the continuing discussions of different types of aspects of the origin and evolution of the moon, followed at the end by future exploration of the moon, the road ahead, in which Apollo 17 lunar module pilot Jack Schmitt will deliver a lecture on his trip to the moon, his field work on the moon, and also what he sees as the vision ahead. As you know, Jack is very active on the National Space Council and is a very important visionary for how we will, in fact, explore space in the future. So thank you very much for tuning in. If you have any individual questions, please don't hesitate to email me, and I'll be happy to try to answer them. Thank you very much for your attendance, and again, thanks to everybody at SSERVI and to the people at Ames, Ricky Guest and colleagues who makes all this possible. Thanks for today.